Layton Carasik, thank you so much for facilitating this, bringing me down to Virginia Commonwealth University, setting up the seminar. Can't thank you. Taking me out to lunch. Can't thank you enough. This has been awesome.
Well, I'm glad. I'm glad you had the opportunity to come down, and since we're so close to DC, it didn't make sense not to try to get you down here. So
yeah, this is great. You're kind of an interesting guy, super young, but you've already had like so many different experiences in industry, academia, big industry, startup world. I mean, you've been all over the place. So it's going to be super fascinating to hear, how your perspective has been shaped over time. But before we get into all of that, as we always do, tell us how you first learned, got excited about nuclear engineering to begin with.
So this started when I was at community college. So in 2008 is when I started a community college degree where I was still in high school at the same time. And I had one of the faculty members who was teaching math. He found out I was in one math class and he said, switch to my college algebra class. So I switched to his college algebra class, and he later let it on that he was like, oh, I did my master's and PhD in nuclear. I'm a math background, but he did that to then go into industry, and he was in industry for like 20 years. Well, he became a really big mentor of mine while I was at community college, and eventually I was looking to transfer into mechanical engineering at Georgia Tech or other institutions. And he said, why not nuclear? It's like, well, why not nuclear? It's like, all right, well, let me go look into it. So I looked at it. I was always interested in clean energy and how we can positively impact climate change and try to mitigate the effects of it or try to move away from the effects of it. So after all that, I applied to a couple different schools, and I got into University of Tennessee, Knoxville for my transfer institution and said, I'm going to go there for nuclear engineering. And that kind of sealed the deal from there, because once I got to Tennessee, I kind of fell in love with the field and said, this is what I'm going to be doing for my career.
That's so cool. Do you remember what about it made you fall in love with the field itself?
I think in terms of the fact that it is such a diverse groupings of disciplines, the fact that I could have gone in and done reactor physics or thermal hydraulics or material science, I could have been working on reactors or national defense related applications, and even all the way to medical applications. It kind of just built that internally to be like, well, it's a specialized degree, but how specialized is it really? Yeah. Plus, I met a couple people before I even started that said, hey, I got a nuclear engineering degree. It was really invaluable, but I decided to leave the field for finance or other engineering. So I thought from the perspective of whatever I'm going to learn from this will still be really useful to no matter where I end up going. And I mean, you've got like Ray Rothrock, who did I say that name right? He's a huge investor. That he was a nuke engineer out of Texas A&M, and I
think he worked at like Shippingport or something in his career. Somewhere in the Northeast, one of the early plants.
Probably. I never got a chance to look too far into his background, but he.
I know Ray actually, ironically, from my Silicon Valley life.
Yeah, that's funny. So like A&M always tried to bring him back to come give talks, and he's sponsored. I think he still is sponsoring a seminar series at the nuclear engineering department there. Cool. So, and having gone to get my PhD from there, it was a really cool opportunity to dovetail and get to meet him. So,
what was your PhD in?
Nuclear engineering.
What did you focus on?
So I focused on the thermal fluid. So how do you get the heat from the reactor to your power conversion cycle? So how do you boil water, basically, right? But my PhD was very interesting in that the first year was pretty much all nuclear engineering classes. But after that, I did like 35% mechanical engineering, 35% aerospace, and then the rest was civil engineering classes.
Whoa.
So because
how did aerospace and civil fall into all this?
So again, going back to this like diversity of all the different subjects. So nuclear being the OG, interdisciplinary degree, right? Being mechanical means the same stuff that we do in aerospace, the same tools, the same information can be extended to nuclear. Same thing with civil. They do internal piping systems. They do open, like water systems. They use the same tools that we use, or at least a lot of the same methods. So they taught classes that I couldn't get in the nuclear department, but I was able to get in aerospace or nuclear or civil or mechanical. I took a lot of heat transfer courses my PhD advisor was a mechanical and nuclear engineer. So he said, go take classes from there because that's what you really need to do. So
cool. Yeah. And then throughout this time, you also had a couple really good internships as well, right?
Yeah. So one thing that probably really started off was between community college and undergrad, I did an research experience for undergrads at Georgia Tech Savannah. I think the campus has kind of scaled back in terms of their activities because of the consolidation effort in Georgia, but that was an opportunity to work on Boeing 787 manufacturing processes. So that was like the first thing where we actually got to go to the Boeing plant in Charleston, South Carolina, and see them build the second massive assembly plant they were building for the 787. The Dreamliner, if anyone wants the formal project name that they had for it. But I did that, did TVA the next summer where I worked at Bellefonte.
Tennessee Valley Authority,
yeah.
Which is a utility half owned by the federal government that's got some nuclear stuff in it.
Yeah, it's a GoCo. I think it's the original GoCo, so government owned.
Contractor operator.
Yeah, so they were one of the few utilities that really tried to diversify a lot of the different types of reactors. So they built boiling water reactors, they built Westinghouse-style pressurized water reactors, they built combustion engineering style pressurized water reactors. They even built they almost finished the Babcock and Wilcox pressurized water reactors, which is what Bellefonte was. And they had 4 other sites with like 14 more reactors that they didn't finish. I think it may be less than that. So someone may say that was wrong, which it's been a little while since I've looked at that. But it was during one of the original slowdowns, like the 1975, 76 era when we started the orders it stopped coming in as fast. And then eventually TVA said, hey, the growth of the energy needs just slowed down. And they just didn't need it. At the same time, they had their coal fleet. They had a little bit of natural gas. They have a lot of hydro in the Tennessee Valley because you've got the Tennessee River and a couple others that they just said, we don't need this right now. So that's why they didn't finish even, I think, Watts Bar at the same time, 1 and 2.
Right, those got finished much later. Those are some of the late ones to get wrapped up.
Yeah, so they were the latest reactors to come online. Or at least Watts Bar 2 was the latest reactor to come online in 14 or 15. So it's really cool because there's all these great sites that TVA could go to and say, let's build these reactors. It's just, we've got to go back to the case for it. Do we have the economics for it? Do we have the power growth for it? For a little while there, it looked like with the push to get us as far off as fossil fuel as possible, that TVA would say, well, we're just going to go back and finish a lot of these plants. They're still perfectly good. We just have to go basically do a huge restoration / refurbishing effort, make them like new of day 0, which is when I was at Bellefonte, that was a lot of the discussion.
Yeah, so what were you doing at Bellefonte?
So I got to basically run around in containment for an entire summer. So it was really cool. So I showed up day 1 and they said, here's your hard hat, here's your training, go train for 2 weeks. And then you're going to do a lot of walk downs, look at plant drawings, see what's there versus what is actually listed. I did a lot of communication between TVA, what was Areva, now Framatome, because Framatome bought I think it was the part of Babcock and Wilcox that had the construction, or not the construction, but like the intellectual property around those pressurized water reactors, because those are the Babcock and Wilcox style. And then also Babcock and Wilcox Canada, which is where they were doing a lot of the heavy forgings or assembly for replacement steam generators. So they were going to go into Bellefonte, cut out the old steam generators, because what had happened back 20 years before, in the 1990s, I think late 1990s, they went in and cut out all the steam tubes. And any type of investment recovery, they did that steam tubes, any of the major piping, things like that.
Wait a minute. You're saying that back then they were shutting it down and they're like, wait, we sell precious or valuable metals in here, so we're just going to go in and chop it out and reuse it?
Well, they never actually turned those reactors on, right? Yeah. So like they had delivered fuel to Bellefonte. They had, I think Unit 1 was 90.
Fuel? Why didn't they turn on then?
I don't remember what they were still 77% left to completion.
What?
And that
so
was
close?
I know, yeah. So they could have had at least Unit 1 on, and I think Unit 2 was probably close to like 50 to 60% completed. So they have, if you go back to Scottsboro, Alabama, you can actually see the 2 massive containment buildings. If you can, and you can walk into it, you can still see a lot of what was left there. I think they did the final investment recovery a couple of years ago, where they said just whatever else that we can sell off to recover what we can, until the recent investor bought the, I think maybe there's some things going on still, but I think it's been bought by a private person, the land. So, because I know that there's a kind of an idea to go back and actually not finish those reactors, but build a different set of reactors there.
Nuclear reactors?
Yeah.
So a private person bought land to build a nuclear reactor there?
I mean, I would hesitate to say that, like, let's confirm it's going to happen, but
Let's get some juicy details.
I know. I'd have to. I mean, look on Google. That's the best thing I can recommend because I can't remember the person's name. But
Yeah, cool.
they're apparently a very big name person from Chattanooga. So
Cool.
yeah. So I actually lived in Chattanooga, Tennessee, and commuted an hour back and forth because it was four 10s that you work 10-hour days, 6 to 4, go home, and then I'd have the entire 3-day weekend to go.
Sweet.
Either hang out in Chattanooga or go to Atlanta where my family is, or go to Tennessee or go back up to Knoxville.
Why aren't all jobs 410s? Like, wouldn't that be better quality of life for literally all Americans?
I think if we could get a confirmed 40 hours and only 40 hours, that would be great. But I think the problem is,
why don't we make every Friday a federal or every Monday a federal holiday of some sort? You know, pick our favorite leaders, rearrange a schedule for some stuff, and just have a bunch of 3-day weekends.
I fully agree. But at the same time, as a junior faculty member, especially, every day is Saturday, but you work on Saturday, right? So it's what you.
I know.
You can take a Tuesday off, but you're working the other 6 days or the other 5 days of the week that you need to cover that. So, but no, I agree. I mean, the context in terms of how much work you can really get done versus how many hours you need to work is always. It's a hot button issue, but that potentially is getting a little bit more political.
Okay, so you pursued your PhD in heat transfer, essentially. Was there anything that kind of you felt like by the end of it you were just uniquely expert in?
I hesitate to say expert because I feel expert is someone who's done something for 30 years. But I would say in terms of computational modeling, specifically high fidelity computational fluid dynamics and more design level computational fluid dynamics. So things that you would either run on a supercomputer or your local computer. So if I'm a designer at, let's say, Westinghouse, and I need to do a computational or CFD run is the shortening for it, we would say, all right, what can we actually run on locally? So we're going to do one tube as opposed to an entire tube bundle. That's where I would do design level CFD. If I'm doing high fidelity CFD, I'm running as much of that tube bundle as I can on a hero class supercomputer like Murad Argonne or Titan, which I think is going offline now at Oak Ridge, or some of the other ones out there.
Yeah, when you say supercomputer, you really mean the largest computers in the world.
I mean top 25 out of the top 500 supercomputers. Ones that if we finish at Argonne or Oak Ridge or INL or the NNSA labs, National Nuclear Security Labs, administrative labs, sorry. These are ones that when we finish them, they go at the top of the list. They are 500,000, 1 million, individual cores that we're running on. So these are ones that we keep realizing we need more and more computational power.
Yeah.
So,
crazy.
yeah.
And then you got into the startup world.
Yeah. So I think it would be cool just to say, because I've got to give Dr. Eric Lowen from GE this credibility. So
he's an original 5 Titan. Yeah.
Yeah. So if Eric ever hears this, I met him when I was an early undergrad at Tennessee, and I asked him what is the best advice for my career. He said, go do research at your institution when you're there. Go to a national lab, do a summer there. Go to utility. Go to a vendor if you can, and then do regulator. Do at least 3 of those. So I hit 4 of those. I didn't get the regulator, but and in the case of I did TVA, I did Westinghouse twice. I did Argonne National Labs, Livermore National Labs, and I went to Imperial College London for a summer and worked there as a visiting researcher.
So cool, man! You just bounced all around. So Eric was the one who told you to do that.
Yeah, he was the one. So I don't like
kudos to him.
Yeah, I don't like to say that I like to bounce around too much, but it did give me a perspective across the country. And having Eric say this is a way to get your job to be more a career, that helped me say, okay, just because one of these things wasn't as good of a fit for me, maybe one of these other types of jobs is a better fit. So for me personally, the realization was national labs or universities are really where I shine. industry or industry in terms of utility or vendors, it's important work, but for me, it's just not the best place for me.
And why is that? Why do you shine in the academic setting?
I have a lot of ideas that keep shooting in my head. A lot of them are bad, but some of them are good. And I really enjoy the ability to generate those ideas and to try to get into the nitty-gritty details of it, and to kind of drive research in one way or the other.
Cool.
Pending, or like the DOE/government priorities play into that, but at least I can generate how we get there.
You just said something there, though, that struck my mind in a funny way. Pending that the priority is play into that. What if the priorities are wrong? Like, what if you've got an idea of what you think is important for the industry, but that is not in line with what today's priorities are? How do you manage that? How do you deal with that?
I mean, you've got a couple different avenues. So as faculty, in terms of the specific research topics, there's these mechanisms called requests for information that, for instance, the Nuclear Energy University programs, CINR proposal call, that they just issued the one for this year. For the give out next year, they issued this fall. They have an RFI that you can write in. I think these are important things we need to address. And industry can do the same thing. So anyone can contribute these short white papers to say, these are really important. From a upper level, that really gets into advocacy. So if I think something is really important as a private citizen, I would go talk to my legislators, so let's say just on the federal level, let's start there. I would go to my House member. I would go to my 2 senators. I would try to talk to people in individual entities if I can, or the committees that are relevant for energy and water or science and technology.
What do I do? I'm in DC. I don't even have senators I'm allowed to go talk to.
Yeah, I know. I mean, DC statehood is a really interesting question. It's just weird.
Is it going to happen, do you think?
Probably not for another decade. So the thing about some of the other the other territories that we have, is that the rest of the country does. So for instance, Puerto Rico, the rest of the country is pretty favorable towards Puerto Rico becoming a state.
Yeah.
For DC, it's very popular internal to DC, but a lot of the rest of the country is just why would we do that? And
we barricade the roads and don't let anyone go to the Congress building until.
For what it's worth, I think some people would prefer that in some states. So just keep everyone in DC.
We got off topic. Sorry.
Oh no, that's fine. No, but in terms of representation with taxation without representation, that's ridiculous, right? That's the entire foundation of our country. And the initial idea behind DC has completely changed since then. But getting back into advocacy, if we want to realign our priorities, for instance, if we want a national energy policy in the United States, we need people advocating to their Congress people, their senators, their House members, the White House, in terms of whatever mechanisms exist for that, and say, we need an energy policy that includes nuclear, that includes these other energy sources, and this is why. What your reasons are is entirely up to you. For me, I believe that we need to prevent climate change from destroying our planet and having major catastrophic consequences on our society.
Preach, brother.
Right? So my thing is, I want nuclear, but I also fully believe in, if we need a mixture of things to get us to that endpoint, whether it's solar, wind, natural gas, coal's off the table, hydro, what we can do. Well, I mean, for instance, if I take a coal plant and I replace it for an equivalent natural gas plant, you've now taken and only have 1/3 the emissions.
Yeah.
Right? So
I'd love to just shove a nuclear reactor in there.
I agreed. But from a standpoint of a utility that says, well, I can just build really cheap natural gas, why am I not just going to do that? We have basically a supply of 200 or 300 years worth of just in the United States.
I know,
I can meet my climate or my carbon emission goals for the next 20 years.
But the goals are not the right goals.
Agreed, right? Yeah. So the goal should be fully decarbonize by 2030, right? Or something sooner, because we're starting to see, if we can do sooner, we're starting to see more and more impactful weather changes, and it's starting to escalate.
Yeah.
So, I
Seeing
mean,
it real bad.
I've got family that lives in Florida. I've got family that lives in Charleston. And, well, I've asked my sisters, hey, would you be willing to move? And they said, no, we don't want to.
I'll tell you what would make the move. If the government wasn't subsidizing the insurance down there, like economics alone would force people to move. I feel like we're subsidizing people being in harm's way. We
are, but I do think you do. I mean, you have to think about some of these people have lived in those places for their entire lives.
What do you want me to
No, I know, but it's a cultural understanding, and it's also an economic impact of, are we as a country willing to accept that if we want to move, if we don't want to mitigate climate change appropriately, and even if we do, we're still going to have the next 20 years of what the impact would be. We have to convince these people, and we have to commit real hard cash to getting these people out of their place and not just leave them high and dry.
Right.
We need to leave them, or we need to get them into a new place, seed them with or get them a new house or a new way to start their life. For instance, there's jobs in Florida that don't exist in Alabama, right?
Yeah.
And like Alabama has a lot of great land that you could settle in, right?
Yeah.
But there's no job for a lot of nukes in Alabama. There's some, so like Plant Hatch is there, but like we don't need more than, we only have so many nukes that need to work at a nuclear power plant, right?
Yeah, that's true.
So we have to commit from a policy perspective, from a executive branch perspective of, are we going to resettle these people? Are we going to mitigate these challenges? Are we going to fix these things? Or are we going to just keep letting this happen where the most disadvantaged people are stuck there, or they just really don't have an out. And we're just going to accept the fact that a lot of them are going to lose their livelihoods. They may lose their lives. Their lives will be permanently impacted from now on. So this kind of went off rails in my train of thought. So
no, it's okay. No, it's fun talking to you because you're like half nerdy engineer, but then half super articulate policy person. How do you think you develop that cross-functional skill set?
So I come from a family where both my parents were business administration / accountants. And the first, all three sisters are involved in education in one form or another. The oldest sister actually lived in Silicon Valley for quite a while and worked as someone in that area, but now she's moved into education. So she's actually the director of education tools for her new company.
Cool.
And she's building her team and everything. So but she's been in this educational role for a long time, just from an industry side. My other two sisters, one of them is a middle school science teacher and math teacher at a Montresor school now, in Charleston, South Carolina. The other one is, she's not a high school teacher anymore, but she was a really popular AP Psych teacher in South Florida. And she now works for a couple of academic entities that she provides, she does online classes for them or what have you, but she also does a couple other things in her career. So
family.
Having them in my life as trying to force me to be less, or to not just be solely focused on science and math, because I said this before to you, STEM is really important because it helps us do the fun things like arts and science, or arts and music.
Yeah.
If we can't have one without the other, I don't do all this because I want to go home and think about more science and math at home. I want to go home and enjoy arts. I want to enjoy.
What are your artistic passions?
I think if I had enough time, I'd probably do a lot of drawing. I do like listening to a lot of music. I don't make any music, but a lot of, if academia never worked or the nuclear field kind of I decided I wanted a big change, that's potentially the path I would go into. But I was raised in a generation of video games, so I love playing video games. So that's not art, but it is art in some sense.
Sure.
There's a lot of really beautiful art that's in them. But in terms of activities, those are a lot of the stuff that I would get into. I also, I would potentially even look into more of architecture type of things, because I really like the design of buildings. So from an arts perspective, it's associated with a more construction aspect, that would be kind of cool. But that's not something I do on my own. That's just a random thing. So.
Cool. So now you're here. in the academic world after having gotten a taste of a little bit of startup world, a little bit of industry. What are some of the lessons that you wanted to kind of take from that experience to bring back to your students?
So the starting out one is particularly with design. Making that connection of theory to the actual design aspect, because so much of my experiences in startups and other industry aspects is, how do we actually connect to someone? Why are you calculating the Reynolds number of a flow? Well, the Reynolds number ties to potentially how big your pump needs to be. If my Reynolds number is too high or contributes to too high of a pressure drop, I suddenly either have to get a bigger pump or I have to redesign my entire system. In terms of the actual design process, there's a lot of people who say, let's start senior design with like CFD and like neutron transport solves and all these like really high fidelity. That's not how you do it, right? You do your initial proof of concept to say this works, but really you want to do pen and paper, 0D hand calculations, right? Or the scoping calculations, right? Ideally, you're doing it scripting. So Dr. Katie Huff at University of Illinois Urbana-Champaign will hopefully hear this. But like Python, like write your Python scripts, like do this so that you can do rapid calculations, because you can build out, okay, what's my heat transfer correlation? I can do that a lot faster than trying to simulate flow in a pipe with CFD for the scoping calculations. Same thing with reactor physics, point reactor kinetics. Do the simplify the system as a point. Do all of that together to map out your design space. From there, we then decide, okay, is it possible? Yes or no? What's the next step? The next step is saying, okay, out of all those points we mapped, and this is not possible, but this area right here is possible, which one is the most favorable we want to go with? We take that design point and let's start designing the reactor. Will the reactor physics work? Are the materials actually possible to buy? Or do they make sense to try and make it happen? From the fluid side of things, do we have the appropriate pressure drop correlations, heat transfer correlations, other fluid type of behavior correlations, or are we outside the bounds of them? Which is what a lot of startups, I believe, are facing, where they're really saying, well, like the Diedis-Boelter heat transfer or Nessel number correlation is great, but it's really only meant for pipes. Straight circular pipes. That's it. Of a specific Reynolds number range, of a specific Prandtl number range. But if you're trying to extend that, the Reynolds number range of this changes in terms of like when you transition from very ordered laminar flow to turbulent flow, depending on what your pipe looks like, depending on what's the if there's obstacles inside of it. So for instance, if you have a pebble bed reactor, so let's take Kairos Power or X Energy or some of the previous German designs, your transition number is very low.
What's the transition number?
It's closer to 100.
No, what is a transition?
Reynolds transition. So you've got a range. So you've got laminar to turbulent, and then the transition region between the two.
And that's describing two states of flow.
Yes. So ordered flow versus highly chaotic / it's kind of not chaotic, but and this transition is a big deal to figure out where it is, because you really don't want to operate in this regime, because depending on what type of geometry it is, it's very unpredictable heat transfer behavior. It's very unpredictable pressure behavior or pressure drop behavior or behavior that would contribute to the pressure drop. Depending on where this point starts, could heavily impact what you're going to see in the behavior of your reactor. So for pipes, it's like 2300 is about approximately is what some people use 2000, some people use higher. For pebble beds, I think it's closer to about 100. So if you're wanting to operate at a turbulent regime of flow, you don't need to have it as high. But also, depending on what coolant you have going through it, so for instance, if you go with gas, you want to limit the pressure drop, because if your pressure drop is too high, your circulators will just eat up how much power you're actually producing.
It'll be almost like a parasitic load on the on the reactor power plant itself.
Yeah. So for instance, let's take a monolith like 1 megawatt pressurized water reactor.
Yeah.
Their pumps contribute about 2 megawatts of heat into the system. So when they're doing startup in some cases, or at least is what I thought I remember hearing, is they would turn those on just to start getting everything circulating.
Hot,
But that contributes so much energy into the system, it can help heat up the system in a proper manner, right? If your circulators are 10 megawatts each, of your overall, you produce 100 megawatts of power, that's how much of an efficiency cut you're taking on your reactor.
And
that's a lot.
That comes from a more turbulent flow leading to that pressure drop, which means you need to oversize your
So in some cases, but part of it's also due to the fact that you're going through like a highly disordered or even ordered packing of pebbles where it has to overcome that pressure drop. So yeah.
But do we also want a highly turbulent flow for better for like convective heat transfer properties?
It's a trade-off.
Okay,
so there's a curve which shows pressure drop and heat transfer. And ideally, you want a curve where you have higher heat transfer at a lower pressure drop.
Yeah.
Right? But a lot of times it's higher heat transfer at a higher pressure drop. So you've really got to pick that design point or where you can do it. And it changes. So like if you take certain types of heat transfer enhancements, so like let's add fins to tubes, or you add like rifling, where you're basically grooving.
DNA style.
Well, no. Like so imagine the inside of a gun where they have the grooves that help spin the ball, right? Well, you can spin the flow.
Ball. Right? We're not in musket days anymore.
Well,
bullets.
Bullets. Yeah, but I mean, if I was really into the Revolutionary War as a
cannons.
Kid, so.
Cannons.
Yeah. So it can. Yeah. So you can do that. Those would be your heat transfer enhancements. It can make that curve much more favorable for higher heat transfer with a lower pressure drop.
Okay, so you're the heat transfer guy. So you're thinking about this type of stuff in the reactor itself, and then also, there's usually, not always, but usually another stage where then you have to transfer heat between two different types of coolants, right? And that's another place that your field of heat transfer study comes into play, right?
Yeah. So from the minute you generate heat in the fuel is where my research should start, right? Where I have interest in, and I want my research group to be looking at too.
Hey, come? Sorry,
go for it.
Random question, but when it comes up, I gotta ask. How come inside like your standard PWR fuel assembly, how come they're using helium to conduct the heat from the pellet, then to the cladding, then to your water? How come they don't fill the thing with like liquid lead or something that maybe wouldn't create as much pressure when hot, but would also have great conductive properties?
So I can't give you an affirmative answer on that. This is something that I should be able to straight out answer, but I'll have to admit that's something I'd have to go back and look up. But in terms of the actual, from the heat transfer perspective, in this case, radiative heat transfer would probably be one of your major dominant effects in there, but part of it I think is, from what I remember, is related to like fission gas release. So that you, if I remember this right, it's so that you have a different place for it to go as opposed to the fission products diffusing out through the rods. Now, that may not be right. So you'll have to, someone is probably screaming in their ears right now. But
they'll just have to come on the show and explain it.
Exactly, right. This is what happens when you take engineers and say you're hyper focused on everything past the cladding. That's
so your stuff is past the cladding.
Yeah, past the cladding.
Sorry.
I'm trying to get into the fuel side. Right? Yeah. But so part of it too is in terms of like not filling it, you have fuel cracking and swell. So so let's take or uranium oxide fuel. You've got these little cylinders. I'm trying to think of not tabs, but that you then stack, or fuel pin, or
pellets,
fuel pellets that you stack in the rods, and then you fill it. Well, they're going to swell. They're going to close that gap eventually. They're going to crack. That's where the fission gas release inside of it is. So you need a place for it to go.
Yeah.
For other fuels where it's potentially a metallic fuel, where you actually have the ability to have that layering of like a sodium between your fuel and your cladding, or your actual fuel, or potentially another oxide fuel or nitrate fuel where you can do that. That may be more favorable, but it just kind of depends on what you expect to be. I think this is more on the material science side or the mechanics side of the actual fuel itself, of what is it doing as it's experiencing irradiation from the beginning to end of life.
Yeah.
So.
Okay, so you take over from the cladding. So we go from cladding to the coolant. Coolant then moves around somewhere, goes into some sort of heat exchanger typically, or a steam generator, the type of heat exchanger, I guess. So what are some of the considerations there in the heat exchanger stage that we should be thinking about?
So it depends. So if you're doing a pool type reactor, you've got emerged, so sodium fast reactors and some molten salt reactors, they've got effectively submerged heat exchangers inside the pool of coolant. So you've got effectively a swimming pool of liquid sodium or molten salt that you have to design your heat exchanger around that. So our traditional bread and butter heat exchangers are shell and tubes. So a lot of tubes, straight tubes that are then bent, or just straight ones that then connect. And flow going on the outside, flow going through the inside. Those are great, but those can be improved. So throughout history, we've improved with printed, or not printed circuit, but plate and frame ones, where we effectively have different frames that we attach to each other and put sealant or gaskets. Sorry. To conduct that have fins inside of them that they transfer heat that way. You have you get like twisted tubes, which are really cool. You can get those helical DNA ones that I saw recently. But really, you're doing the U-tube steam generators. You're doing the straight tube heat exchangers. So, for instance, the Babcock's and Wilcox heat exchangers are the straight through one pass. They're not doing the U-tube, and they're these like very large heat exchangers. Whereas the ones steam generators, whereas the ones in PWRs are shorter, but that's because they've got the U-tube arrangement. And it just depends on your trade-off. So, for instance, with the Babcock's and Wilcox ones, you should have superheated steam by the time you hit the end of it. You don't need as much like basically moisture removal. So you have these large cylinders that have effectively static or non-moving fan blades, and then it causes the steam to go spin around and then throw all the droplets on the walls. You don't need as much of that with those types of heat exchangers, but they're potentially harder to control from an operations perspective.
Control? Wait, what do you control about it?
Your water level. So your water level may be harder to control in a straight through once through steam generator versus a U-tube steam generator.
Got it.
Yeah.
The water, how does it get into a steam generator? Is it sprayed in? Is it
depends.
Pumped in?
Well, it's all pumped in. So okay. From the standpoint of, you've got feed water pumps that then pump into your steam generator on the secondary side. So Westinghouse and Combustion Engineering have these, like, it gets pumped into a huge ring that goes around the peripheral of the bundle. They have nozzles, or they'll just directly dump water onto the outside of the heat exchanger that will then go.
That's like preheated?
Well, yeah, it's been preheated along the way, and then it's also cooling the outside of the steam generator, such that from a materials perspective, you're not experiencing as high of temperatures on the outside of the heat exchanger.
Oh, interesting.
It can help. It can help keep keep replacements to a minimum in terms of. It can extend the life of the shell of the heat exchanger longer.
Got it.
So similar to, you want your major structural materials to not experience as high of thermal gradients. So if anyone out there is wondering what a gradient is, take black and white as two different colors, and think about the transition between the black and white. The shorter that transition is in terms of going from black to white, that's the higher your gradient is.
And that hurts the structural property of materials.
It can be really bad, because what can happen is that leads to really large thermal stresses. If that thermal stress is high enough, or if it keeps cycling, eventually it's going to break the material, or it's going to crack or weaken it. And once you hit that limit, and that's part of how we determine when we should stop using them.
And this thermal cycling is kind of like bending a paper clip.
Yeah. Eventually you'll bend enough that it breaks. Yeah. So, from the standpoint of, if you can keep your outer structural materials cooler, you can also then use different types of structural material or vessel materials, because steam generator roll, you still kind of have the same type of pressurized vessel too, but it's not as highly pressurized on the outside, because you're highly pressurized, or the steam tubes themselves have to handle an amount of pressure too. In terms of, feed water, then it goes down. It's physically separated until it hits the bottom of the tube sheet where the tubes are coming out. The water comes up. It starts to boil inside the tube. in the tube bundle, and then eventually it'll get to some quality of like 40% steam or 50 or 60. And then it will go up, it'll get into, which is the moisture content. So 40% of 40% moisture content, and then you get into this drier package, the centrifugal forcing package, and then eventually you come out with really high quality steam.
Yeah, how come it only gets up to 40, 50%? Why what has to change about the design of these heat exchangers to get it so the steam is super dry by the time it leaves without having to spin out the water?
Well, from an economic standpoint, I don't know if there's really a large benefit to not having that package up there. But you'd make the bundle taller, or which potentially is a trade-off, is what if that causes issues with because you've got water and steam going past and you've got like high velocity stuff going past, it's causing the tubes to vibrate. If it's taller, it could potentially make it more significant, right?
Does anyone ever have like two stages of steam generators where it's just you kind of link them in series, and that way you make the steam drier over time that way? Is that a thought ever?
There may have been a design out there in the past, but now right now it's just you've got a single one on each leg coming, or water leg coming out of or coolant leg coming out of the reactor. That's your steam generator, and then it goes to your goes straight, or not straight, but it goes to your first high pressure turbine, comes out. Part of that is used to preheat or dry to your dryer to then help dry the steam again and then run it to your low pressure turbine.
Got it.
I mean, the nice thing about the steam generators they really are these like, people give a lot of flack for U-tube steam generators or straight tube steam generators, or why are we building this? Or we had some reactors that got closed down because of improperly installed or issues with the manufacturing. But I mean, they work. They really do. Yeah. When you build them right, they work.
Sure.
And it's going to be the same problem with other reactors in the future of if you have a manufacturing issue or if you have a design issue that leads to the eventual, hey, we have to either replace it or we shut down the plant. I mean, that's just the consequence, right? But like, and that's kind of going into, I mean, I remember very vividly when San Onofre was first shut down, and then them saying, are we going to bring it back up to 70%? Are we not? And then the final decision for them to just turn off the reactors. And
because of the steam generator issue.
Yeah. So it was they had higher wear than expected in the steam generators, much faster, because they had just done an uprate at songs, is what the shortage of it is. The shortened name for it is. Well, they went back and said, we're having to plug the tubes faster, or they actually had a leak where one of the tubes of primary water was leaking to your secondary side, or vice versa, right? And that led to the NRC saying, you gotta fix this, figure out what's going on. Why are you not able to run it? We gave you the power upgrade. We said, that's fine. And then they found out later that there was issues in terms of the manufacturing of how they were holding the tubes together, in terms of like the structural supports and the conditions that it was supposed to experience. So a lot of it, I'm not trying to place blame on anyone. It's just in terms of the end result is that we lost, I think, 2 gigawatts worth of electricity in Southern California, which we have to be better about what we're doing. We have to make sure that from every stage, we always question our assumptions, right?
And these steam generators, they're so big, they're so expensive, they're so like one-off when it comes to these gigawatt scale plants. How come they don't, to make them more easily manufacturable and easily replaceable, how come they don't just put more of them in parallel with each other, of smaller versions that are easier to just kind of like, something's going wrong with one, ship it out to a repair facility, or maybe even dump it and just drop in a new one and have like 20 of them in parallel or something?
Well, that can lead to another set of issues, right? So if you only have to have one component that you have to worry about maintaining, you only have to worry about that one component in that loop. So let's take a 4-loop Westinghouse plant. You only have 4 steam generators. You have to worry about the maintenance and operations of. If you suddenly have series of them, do you have series of them inside containment? Or they have part of it is actually, you still have the same problem of maybe you have one major heat exchanger inside containment, and then every single one outside of it is doing those activities where you have one big heat exchanger that's just going to another pressurized loop, but it's not boiling the water. It's just heating up the water to the point that you then go to smaller steam generators outside on the secondary plant. Right. But that's more capital equipment. That's more operation and maintenance costs. It just trade-off.
It's intuitively
but
to me,
think about it this way.
The economics are better if you've got more, that once you get to that regime of it being a one-off component that's not used in any other industry, that you want to bring yourself back to the point where we're making many of these things, putting them in parallel, maybe even taking an efficiency hit. But because we've got a lot more of them, they're more manufacturable, they're cheaper, they're easy to just pop out if something went wrong, and even disposable, throw in another one.
So in terms of potentially cheaper, for the main heat exchanger, the thing is once you're under a high enough safety classification of those steam generators, or those heat exchangers, that discussion has to be someone who's more qualified and has that background. I remember having the NQA or nuclear quality assurance training and how that relates to, okay, the feed water rings and the steam generator is a class 3, but a class 1 is the actual tubes or something, from vaguely if I'm saying this right. So again, someone's yelling in their podcast ears, but it may not mitigate that impact though. But in terms of, we have so many pressurized water reactors operating today that had successful steam generator replacements. Yeah. They had successful second set of steam generator replacements. That I don't think that, yes, the loss is gigantic, but we can't take a couple of instances and say that this is actually representative of a gigantic problem, as opposed to saying we need to hold ourselves more accountable. We need to actually make sure that when we replace these we know for damn sure they are going to be replaced correctly, and that they're going to come out and we're going to have operating reactors for another 20 years. Or, I mean, originally they were supposed to be run for 40 years, but then they had all these different issues that they didn't realize were going to happen, where once you start having I think it's like 20% of the tubes are plugged. You've lost enough.
What's a tube plugged mean?
So
just don't run water through it?
So when you see that one of the steam tubes, or the tubes going through, that you're running the pressurized water through in the tube bundle, when that has degraded enough based on non-destructive analysis that they do, they then plug the tube. So I think it's like 40%. Once
so it's just sitting there, not being used.
It's just a dead tube, basically. It's plugged on both sides. It's just like heat conduction,
like a pixel on your screen.
Yeah. It's just it's just
get enough of those.
And they've designed these. All heat exchangers are designed with fouling in mind, in terms of corrosion buildup on the outside, or gunk buildup on the outside of the tubes and the inside. They're also designed with. They're over designed. So they have 10% more tubes than they need. Yeah. Because they know by the end of life, 10% is going to be. But what happened in some cases is they got plugged faster than they expected. They experienced operational conditions they weren't expecting, or maybe the materials inside of it were not as good as they thought they were when they first ran it. So we've had some that lasted quite a while. We've had some that lasted 6 years. I mean, it just kind of depends on who the designer was and what they knew. But the ones that they've replaced, it sounds like they should be able to get at least 20 or 30 years out of each of these replacements. And another thing to think about too is, like, take the CANDU reactors, the Canadian deuterium uranium reactors up at Bruce Power, or the ones that they're building in India. They do full refurbishment of their reactor, of those tubes, those calandria tubes, like every 20 years. Like, that is a massive undertaking, but they can do it, and they can do it right. There's no reason why we can't do that with steam generators. And we do it, so.
What are some of the interesting challenges that you personally want to take on in the heat transfer space now?
So in terms of, this like leads into my research area. So in my research group, the FAST research group, Fluids and Advanced Systems and Technology. So right now the main focus is thermal fluids, or thermal hydraulics of advanced reactors. So take your main three: sodium fast reactors, molten salt reactors of either solid fuel or molten fuel, and gas reactors. I have interest in all three. The tools that we use in one are similar to the tools that we use in the other two. At the end of the day, you have similar CFD tools. That's just how you do the modeling changes. You have similar system tools. It's just how you do the modeling in some cases, or you do have dedicated ones depending on how they were written. Or your design tools in terms of if I'm doing scoping design. So right now I have a project that I'm having a student work on that eventually a couple more will work on, that they are building a short set of computer codes or computer programs that will work with each other, that they do the sizing, or they do the basic heat calculations on a reactor design based on just an average coolant channel, and a assumed heat flux profile. So what is your neutron flux profile? That translates into your heating profile, that then you can then learn, okay, can we actually achieve what is the hottest area of the fuel? Where is that going to be? Also, if we add margin to that and say, what if it's 1.2 times that, your factors of safety, or your trying to remember what it's called. There's a better name that we have in nuclear for it, but it's effectively, margin, we apply a 1.2 factor or 1.5 factor. It just depends. Someone out there is, again, one of those like, it's off the top of my head. Once we can do that, we'll have this tool set that can do your average channel, your hottest channel, the hottest channel. The hottest it should experience should be below your fuel, for instance, should be below what you expect it to start having degradation issues that would say, well, you got to shut the reactor down. For your cladding, if you're using water, it's below. The eventual calculation it would do is it below the expectation of departure from nucleate boiling?
And that's when bubbles, so we want bubbles to form along the outside of a hot surface in order to transfer heat away. But departure from nucleated boiling is when you no longer have bubbles, but it's almost like a layer of gas, which now is an insulator.
Yeah, so you're going to have subcooled boiling occurring in pressurized water reactors no matter what happens. Like, it's just, you're going to have it, but they're going to go off and they're going to collapse almost immediately.
That's good.
It's very minimum. It's very small. But you don't want to leave that regime. And that's where a lot of the safety analysis comes in, is when you hit that, and then it starts to become a bigger deal. And then you have to worry about, okay, at what point have we basically, it's irrecoverable. We melted our core. But so this tool, what it will do is it will provide that design data. It will attach to hopefully what will be a heat exchanger design tool that will do basic design sweeps on heat exchangers, and then also ratings of it depending on what you want to do with it. And it would be any type of generic heat exchanger. And what we can do is then say, all right, depending on what correlations we have, what fluid properties we have, what geometry we have set up for the reactor core, we can say, okay, based on what we'd expect for the neutronic side of things, leveraging what's found in literature or colleagues of mine that could contribute to that, we can then say, here's the operating conditions, here's the correlations, here's how far out of bounds we are these correlations, or here's the engineering challenges we expect to come from this. These are the opportunities that we can then translate to our research, the research group. So that's kind of the starting point. And what we can then use CFD for is we can then say, okay, based on what these challenges are, can we simulate it? Why can we not simulate it? What do we need to change? If we can simulate it, how would we know we do it right? If we can't do it, it's okay, what are we missing? If it's two-phase flow, it's super complicated to the point where we've got so many people still working on it, and your main pioneers in the field of two-phase flow are most of your nukes, right? Two-phase flow is when you've got both a liquid and a gas in the same system. Yeah, so you've got bubbles forming, you've got a system dominated by that.
Because I have a more theoretical question I want to ask you. Okay, back in the day, they didn't understand, and we still don't understand exactly how two-phase flow works, but they understood it enough for practical implementation. And they understood it well enough before we even had computers for practical implementation. So what are we trying to accomplish here by understanding everything to like literally what's happening on a molecular basis? If we know what works, and like anything else, they knew how to build houses with wood before they understood how the cellular structure of wood. Yeah,
but we're trying to 3D print houses now, right? So in the terms of like why are we going deeper? reactor? Well, one, there should always be this innate curiosity that we provide support for.
Yes, and I guess my criticism, my question is almost, do we go too, yes, we should always go deeper, but do we go too far sometimes such that we paralyze ourselves from making progress because we feel like we need to understand something scientifically, even if we understand its practical application?
So I'm not a two-phase flow expert, but I will say to all my friends that are in two-phase flow, this is a field where there's still so much left to be learned, and there's still so much meaningful research that can impact. So if we have a better idea over correlations related to boiling or the behavior related to boiling, we could go to higher temperatures. We could reduce the margins. We can have a larger operating space that we can get.
Can't just sorry, now I'm getting a little creative here. How come we can't just set up an environment? Like in rocketry or whatever, they test it till they blow it up, and then they know where their limit is. How come we can't set up an environment, some underground cabin somewhere, Yucca Mountain, whatever, where we just line up a bunch of boiling water reactors and we test them out at higher temperatures, and whichever one blows up, that's where we back it out a little bit?
Well, we don't even need to go back to the scheme where they blew up they let it just crack containment, right? Like that was like I think that was one of the original borax experiments, right? We don't need to do that though. There's a lot of really fundamental, so when I have a colleague take an infrared camera and look at bubbles forming on the surface of a heating element, depending on what that heating element looks like, whether it's scratched up or if it's perfectly smooth or what type of material it is, we learn enough information from that and those fundamental studies that are expensive, that can then influence the correlations that we then use to do our uprate calculations.
And have we gone higher temperatures in boiling water reactors over time? Are we actually using this information?
We are using this information in terms of the actual meaningful. In fact, I may not be able to really speak to it at the moment, but in terms of, it is meaningful, right? Yeah. It's how they're doing the uprates, but the specifics of it, it's going to be higher temperatures, but it's how you translate to higher power, right?
Yeah. How in a boiling water reactor, how high could you go?
What's your materials limits?
Yeah, so you tell me. So it
depends on. Well, it's a mixture of things, right?
Yeah, what would fail first?
I would say probably welds on the outside of your reactor vessel potentially would fail first. Maybe not that. Maybe the actual cladding would fail first. I mean, the other thing to consider is if steam technology is only designed up to some certain temperature points because they're on the same problem or the steam turbine, if its materials can only go up to some certain limit, will destroy the turbine.
Right, but we know that turbines can go higher because like the ultra critical coal plants are operating much higher temperature. And we think one of the deficits of a boiling versus a PWR reactor, pressurized water reactor, is that it operates at a lower temperature. So I guess your efficiencies are lower because you want that higher delta. So it would be nice to go higher temperature with boiling water if we could.
It would be, but I think the overall focus on that I think would be better placed towards, and no offense to the boiling water people out there, towards fluids that really are intended to operate at inherently higher temperatures, right? So when you
swap out the coolant?
Well, no, I mean it's as we build the next generation of reactors, as we complete our Vogels and hopefully maybe one day we can go back and complete Summer. As we, and all the startup companies are saying, well, I mean, you never know. Hopefully it wouldn't be like a Bellefonte situation, but hopefully it would be like we are committing to finish it. Like everyone at Vogel is like, we have all these trained people. Why would we not go back and finish those reactors? But that's just random thoughts out in the ether. So if anyone wants to pick that up.
I was too dismissive. I take it back.
Yes. But in terms of for instance, a lot of the startup companies are saying we want to deploy these in 15 years if they can. Now, some of them are going to look kind of like replacements where you basically took a pressurized water reactor, replaced the coolant, put molten salt in there, and then changed out all the other components. But or we have operated high temperature gas reactors before. We really have. It's just there's a lot of engineering.
Britain is a leading expert.
I think there was a weird realization as an undergrad when I was like, wait a second, we've already been operating advanced gas reactors for who knows how long in the UK, or I mean, we know how long, but like
since the beginning.
It's not necessarily a new concept. We have operated
advanced gas reactors.
Well, they've got the gas-cooled reactors, then they've got the advanced gas-cooled reactors, which I think is like a higher temperature and like operating conditions for their.
So what's your favorite? I'm going to put you on the spot. What's your favorite coolant fuel combination? From a heat transfer guy.
I stress this from just more of it's where a lot of my current interests lie.
Yeah, tell us.
But I will also say that all the others have really fun things related to probably molten salts.
Why do you like molten salts?
I think there's just something inherently cool about a coolant that you could either say, hey, it's a coolant salt, or it's a fuel salt, or we could dissolve our salt into, or our uranium or plutonium or whatever you want to dissolve into it as your fuel, right?
And what do you like better, the chloride or the fluoride versions? What's your favorite flavor?
I don't know.
Come on, what's your favorite flavor? Come on, you got a favorite flavor.
No. So if I wanted to put salts in a lab, I'd probably pick a chloride, just because fluorides, and particularly if you're talking about like a beryllium-based salts, you just have so many more controls that you need to worry about. Whereas with chlorides, it's not necessarily significant. You have to worry about chloride gas, right? But so you have to limit the formation of that. But in terms of the actual like experiments you want to do, if you wanted to work with them, chlorides would probably be more preferred. So picking up chlorides would potentially be easier in the lab, but I also am of the train of thought of there is a lot of fundamental things we can do with surrogate fluids. So for instance, back when we were designing the sodium fast reactors, they did experiments in water for matching hydro effects. So looking at how is the fluid going to behave as long as you match the Reynolds number of the non-dimensional parameters. So take your Navier-Stokes equations, which describes fluid flow of different kinds, take your energy equations, and then make it so that they don't have any units. The numbers that pop out to provide that are the ones that you can then kind of interchange, assuming continuum assumption and everything else, or like liquids to liquids, gases to gases, right? If I have two liquids of the same, under experiencing the same range of Reynolds numbers that determine whether you're laminar or turbulent or what state it's in, and Prandtl numbers, which is a measure of your convective versus conductive heat transfer occurring in the fluid, you can then say, all right, well, if I have a molten salt that does this, or I have a sodium that does this, that has a similar Prandtl number to water or some other fluid out there, that I can run the fluid at a lower temperature and actually have it in a lab where I don't need a massive system. I don't need necessarily the same type of chemistry control or anything else, and I can still do those same types of experiments. I can at least have some data points on the map or on the design space map to say, at least we have an idea of what we're getting to before we do our actual like test run with the molten salt, with the sodium, with the high temperature gas or other coolants out there.
Yeah.
So cool. I also, let me put this out there too, because I think this is a great way to dovetail in. I truly believe that if one reactor company is successful in building, advanced reactor company is successful in building a new nuclear reactor, new type of nuclear reactor, all companies will benefit.
Hallelujah. I could not agree more. It's in this space more than any, it's a rising tide floats all boats type thing. Yeah. You're going to see a rush of investment. If one can prove at the economics on any new design, you're going to see a rush of investment flow in, because every investor is going to want their competitive design and see how it works.
Exactly. Yeah. I mean, that's why
there's got to be a little bit more, and you and I talked about this before. I think the startups need to be a little bit more open with their information, not so secret. I think they're only hurting themselves with a secrecy. Yeah. Like your trade secrets are not whatever you think they are. They're like the internal know-how of your company, getting all the way to being a successful company. It's not what your coolant or your enrichment percentage was.
Well, for what it's worth, if you are an engineer with enough experience, whether you've worked at other places, you can kind of start to guess some of the conditions, what the salts may be. I mean, it's the same, or the operating fluid. I mean, if you're a sodium fast reactor, people know what the sodium is going to be, right? At that point, if we had 15 sodium fast reactor companies competing with each other, everyone's like, who cares? We know what our sodium content is going to be because it's the sodium. Yeah. Maybe someone's doing potassium chloride, or NaC, or sodium potassium, but like, does that really make the difference? No. And a lot of them have the same engineering challenges. So all sodium pool type reactors have thermal stratification and thermal striping problems. That's all something I've done a lot of work in.
What is a thermal stratification?
Thermal stratification and stratification in general, sorry to cut you off, is the layering of a less dense fluid, whether that's, so let's say you took sugar water and water, hot water and cold water.
Like the bottom of the ocean versus the top of the ocean.
Yes, exactly right. It's the layering of it. It could be based off heat transfer, which would be, or temperature, which would be thermal stratification.
And it prevents convective flow throughout.
Yes and no. It kind of depends, but there's transient thermal stratification, which it can change. There's static or stable thermal stratification, which you may actually want that depending on how your setup is. But in terms of like having it as a challenge, if that stratification isn't predicted properly, you then run into that thermal gradient occurring off of your materials where they just keep stressing.
Yeah. Crazy.
Yeah.
And what was the striping?
Striping is where you have, so it's hot and cold jets, where the hot jets they're kind of cycling on a material. And then that, again, going back to that cycling.
Material layer, crazy. Yeah. Okay, listen, you and I could talk forever, and we'll continue this over beers in a minute, but since we only have so much time on the podcast, as we wrap up, can you paint the picture for what you think the future of this technology is and why you think it's important?
Well, I think it's important because we need to save the world. We need to save the world from climate change. It's gonna happen. I think in terms of the future of the technology, China is starting to approve new builds again. I think Russia is going to keep building. Other countries are going to buy these reactors from somebody. It's whether it's us or others. And I think, for instance, I'm optimistic South Korea will decide to start building again. And hopefully Japan will too, but there's a lot of cultural and political reasons why they wouldn't want to. Here internally in the United States, I think a lot of our success will depend on the policy side of things. If we hit the point where it is truly a bipartisan issue, like we've had with a couple of the recent bills that have been passed, that are supporting the development of advanced nuclear reactors, if that keeps pushing, that will start to help flip the script on the economics argument. Because if the government is starting to help provide the support for technology that other governments are doing the same thing, that will really make it possible for us to deploy these new nuclear reactors. At the end of the day, we're the largest source of clean energy operating in the United States. And I just don't see the advancements currently in solar and wind and other renewable technologies to get us there without having to supplement it with natural gas. This way, we could do minimal natural gas, have nuclear, and then also keep developing those other technologies. So society one day can decide, do we go with nuclear? Do we go with renewable technologies? Or do we want to stay with the fossil and suffer the consequences from it? So,
Carasik, thank you so much.
Thank you.